Hello everyone, my name is Bingyu. I am a PhD student from Illinois Institute of Technology. It's my great pleasure to present our work, Efficient Private Divisible Double Auction in Trusted Execution Environment. In this paper, we study the divisible resource allocation problem. That is, we have divisible resources. For example, electricity resources, storage space of cloud, or stock share, and even bandwidth of communication link. For generic divisible resource allocation, the problem is to find the allocation. We have a set of agents and the divisible resources. Each agent has a valuation function and aim to maximize the social welfare. However, the system does not have valuation function of each agent, since the valuation function is private information for all agents. Instead, we use double auction, which works as a resource allocation mechanism. In this paper, we start the divisible resource allocation problem by double auction. The double auction requires each potential buyer and seller submits a two-dimensional bid profile. It includes the bid price and the maximum amount to buy or sell at the same time. And the auctioneer determines the optimal allocation for all agents and the bid price. Here are some related words for auction. Compared with other auction words, the proposed new framework ETA is a new auction framework that functions the sealed bid double auction for divisible resources based on the trusted execution environment. It could guarantee the truthfulness and privacy with a high efficiency in divisible double auction allocation. For the divisible double auction, in order to ensure the truthfulness for all agents, we co-design the double auction based on the VCG mechanism. Then, no agent, neither potential buyers or sellers, can gain any additional payoff by changing the strategy, since the best respond into the natural equilibrium in the auction game. We denote the payoff functions for buyer M and seller N separately based on VCG mechanism. That is, the payoff function is the valuation function and cost functions minus transfer payment. Valuation function and cost functions can be different. It depends on real-world application. More details can be found in the paper. In terms of mechanism design, we co-design divisible double auction program X. The program ensures that all the bid profiles achieve the best response in multiple iterations for natural equilibrium, and eventually converge with the termination condition. In the initialization phase, while executing program X, the bid profiles of all buyer sellers will be checked to guarantee the maximum buyer price is greater than its minimum seller price. Otherwise, it requires all the agents to update the bid profile. Meanwhile, it ensures that the potential amount of resources in auction is smaller than overall demand and supply. The auction will start once, and the above conditions are satisfied. For iteration phase, given the potential amount of return from the initialization, the updated potential amount can be iteratively derived. Last phase is the best response. The auction program will find the best response in each iteration and finally converge to a natural equilibrium. In this dynamic auction game, all buyer and seller will compute the best response to the current strategy of all other agents. However, there are some privacy concerns may arise in double auction. For instance, if a bid profile, amounts and the price are disclosed, other agents may be able to win more payoff by reporting untruthful bids. Such violations of truthfulness would divide the market, the exchange in divisible resource rule. Even worse, agents, buyer and seller, may collect such information from other competitors and misuse such private information. For example, reselling the data. That is, we need to design the divisible double option mechanism while preserving all agents' privacy. There are some existing work use crypto tools to solve the privacy concern issue, but it required high computations and communications, and also integrity cannot guarantee. Therefore, in order to solve this problem, we propose a new solutions by co-designing the divisible double options with Intel SGX, which is a trusted execution environment supported by architecture extension of Intel. Here is a little background of Intel SGX. SGX is a recently released trusted hardware technology from Intel. It implements an abstraction called the trusted execution environment. You can think of this trusted execution environments as security box or so-called enclave for a program. Once a program is running in this secure box, you will have nice guarantee. First, you will have integrity guarantees, meaning the control flow of your program will not be tampered with by other software running on the same machine. Also, you will get the confidentiality, meaning that no one can observe the internal state of program. SGX has also another important functionality, that is remote attestation. In a nutshell, attestation is a signature and a security key is only known to hardware, and the message being assigned here is a program itself along with user's data. By verifying this attestation, a remote users can make the program is running on the generic SGX platform. So with help of attestation, we can establish a secure channel with a remote SGX platform. So we design ETA framework as shown. There are 4 main components in ETA. Enclave is used for protecting program, codes, and data, which guarantees the confidentiality and integrity of computation. Remote attestation allows remote user to establish, encrypt, and authenticate channels to enclave. Relay is the interface of Intel SGX. It can be used as physical SGX host, and other components cannot directly access to enclave without connecting with R. Key management communities generates a key pair, public key and private key for buyer and seller. Input encryptions. Private key is used inside the TE components for decryption and preparing for further computations. All agents participate in the auctions, while manager handles all the incoming requests and delivers the results as administrator. Also, TE components will be targeted by the manager. Notice that the manager is not the trusted third party. All buyer and sellers inputs loaded through the secret channel are not visible to the manager. Moreover, it can even derive arbitraries from program or conclude with other agents. However, managers cannot interrupt the correct computation of a program, and it will be punished for the program interrupts. Recall that ETA is designed based on a progressive second price auction. Thus, it has a property like weekly dominant strategy. That is, each agent truthfully participating in the auction would gain more payoff than untruthful response. For budget balance, it requires the total budget of buyer is no less than total payment requested by seller. And also, ETA has a property for individual rationality. That is, all agents will have non-negative payoff in the auction. And most important feature for ETA is a piracy guarantee. That is, each agent's bid profile is kept secret. For agents, they only know the transaction. is executed in 3 phases: setup phase, computing phase, and delivery phase, as shown in the figure. Assume that security channel are established between the TE components and all the buyers and sellers. For the setup phase, the TE initiates the system with initial call and prepares for loading our auction program. Once it receives the initial request, a key pair is created, and then the public key is bounded to the TE program by initial attestation will be distributed. Meanwhile, the TE will obtain the key pair from the key management committee and distribute the public key for agents to encrypt the inputs. Notice that all buyers and sellers send messages through security channel. The manager is responsible for batching the transaction of all inputs from all buyers and sellers. Also, validation of messages will be checked by the managers. If it is valid, manager will forward all requests to the TE component. Otherwise, once malicious behaviors are detected, the deposits will be stored in TE for next computation instead of refund. For the second phase in ETA, TE components handle the incoming requests in parallel. TE components retrieve the program with resume call and decrypt inputs with a private key. The execution of auction program is conducted in the sandbox environment on Cave. Then, the software adversary and a physical adversary cannot interrupt the execution and monitor the data live inside the enclave. The results of the program is a secret output, which will be security returned to the manager with a black box program execution. The last phase is delivery. Once execution has been completed inside the TE, the output of all buyer sellers in the divisible double auction is generated, and signature is provided to prove its computation correctness. As a result, the output messages will be delivered to corresponding honest buyers and sellers by the manager. For security analysis, Intel SGX enables the program executed inside enclave security, and adversary cannot interrupt internal computation and state. As for the data stealing, the input data will be encrypted and decrypted inside the enclave. Once it finishes computation, the encrypted outputs will be distributed. Also, once the delivery rule is interrupted, the malicious managers will get a punishment. In this session, we evaluate the performance for ETA in Graphene. Graphene is a lightweight guest OS designed for minimum host requirement. Application can be protected in hardware encrypted memory region on Microsoft Azure. Specifically, considering energy trading as experimental application, we conduct experiments on real power consumption and generate data, which can be used for application of energy trading in peer-to-peer mode for 200 agents, each of which is neither buyer or seller in divisible double auction. We evaluate system performance for ETA and demonstrate results for both auction performance and system efficiency. The left figure shows the total runtime on different number of agents in the auction. The auction includes both the security computations for optimal allocation and peer-to-peer trading in TE. It takes up to only 10 to 15 minutes for 200 agents, even if it adapts for very strong security. Moreover, right figure illustrates relationship between the number of agents and the throughput. As the number of agents increases, the throughput increases linear as figure shown. for evaluating the efficiency in multiple auctions. We use the key size as 1024 bit and 20 agents in ETA for continuously executing 720 auctions. It ensures that runtimes for each auction lies close to 1 minute, which indicates that is not much latency if we execute multiple auctions in real time. For the case study, we execute the ETA for divisible double auction among 12 buyers and 8 sellers with criteria for allocation, quotation amount, and social welfare with different iteration. Due to the space limit, we illustrate the results of 5 representative agents, 3 buyers, and 2 sellers as table shown. The allocation of all agents will increase, and finally they all converge to the final allocated amount after several iterations. Second, quotation amount decrease until the converge. Third, for social welfare, it derived based on equations in the paper. It has increasing trade in multiple iterations and eventually cover to maximize the social welfare. For the conclusions, we design an efficient and private system ETA, which securely executed double auction for allocating divisible resources among distributed agents within Intel SGX. The auction mechanism in ETA ensures the privacy and truthfulness. The input data of both the buyers and the sellers in the auction can be projected inside the enclave. The experimental results have demonstrated a high efficiency for ETA to privately execute the divisible double auction. Okay, that's all for the presentation. Thank you so much for attention.
I'm so honored to attend the EAI AC3 2021 International Conference, and so pleasure to be with you to communicate academic questions and ideas. The title of my academic presentation is Parallel Implementation and Optimization of SM4 Cryptographic Algorithm using CUDA. Well, I want to introduce myself first. I come from Guilin University of Electronic Technology, Guilin City, China. The content is as follows. You can see that. Okay, first of all, I will introduce the development stage. In 2007, Maversky first used CUDA to accelerate the AES and proposed a T-table to improve the performance of the cipher. Since then, most of the team's work mostly follows their scheme. In 2013, Joe aimed at the shortcomings of the ECB mode of AES and improved the results based on CUDA. Then, Fei accelerated AES under CUDA, and the acceleration obtained was about 3 times faster than that of Maversky. And for the first time, he analyzed the performance from the perspective of acceleration efficiency. And recently, Li implemented SM4 under CUDA and discussed different thread block sizes and plain-text block sizes, and obtained a speed-up ratio of 26. As we know, CUDA is a new computing unified device architecture to applicate the GPU as a data parallel computing device without the graphics API mapping. It is suitable for multi-threaded program modes. The CUDA uses the CPU as the host and the GPU as the device, allowing the CPU to call the GPU and the GPU to run the complete computationally intensive part of the program. The CUDA programming architecture is shown in Figure 1. There are 6 common memory structures in CUDA. This finger is the memory structure of CUDA. Each type of the memory has its own scopes and characters. A register is the first storage unit, but the number of it is small. Variables that can't be allocated to register will be overflowed into local memory. Register and local memory are private to each thread. Shared memory is the public memory of each block, available for each thread of the same block, but it might cause memory conflicts. Constant memory and textual memory are read-only memory, but textual memory is mainly used for graphic processing, while constant memory is a special cache which is suitable for data processing in uh, cryptography. Global memory is the largest memory unit in GPU. All threads can access it, but the speed of it is also the slowest. Therefore, for the storage of data variables of different sizes, it's necessary to consider the various characters of the memory structure and select the uh, appropriate appropriate uh, storage structure. Then we will talk about the SM4. SM4 was first proposed in 2006 and became China's national cryptographic industrial standard in 2012, which is adopted with unbalanced general file structure. The block size and key size about 128 bit, and the number of iterative rows is 32. The structure of SM4 is shown in this figure. We can see that the basic process is to first divide the 128-bit key into 4 groups according to a group of 32-bit, and then generate 32 groups of 32-bit wrong keys according to the key expansion algorithm. Then divide the input 128-bit data according to 32-bit. One group is divided into 4 groups and then performed the loop operation. The encryption and decryption process of SM4 is exactly the same. The only difference is that the decryption key of the algorithm is obtained after reverse conversion of its encryption key. Next, I will introduce the parallel design of SM4. About the parallel granularity thread and grid allocation. Through the computation of fine-grained and cross-grained designs. It's found that the performance of cross-graded through the scheduling is better. That is, a single through the process 16 bits better. During the upper bound of threes is 1024. We tested that 512 cells per block can achieve the best performance, and we set the size of grid is the size of input divided the number of threads per block divided the size of the plaintest block. And about the data allocation is the simplest way to put the plaintest Xbox FK and CK into the global memory. However, the access speed of the global memory is very slow, while the storage capacity is large. So the global memory is suitable to store the plaintext. Through compression tests, it's found that storing the plaintext into the global memory and the Xbox FK and CK into the constant memory have better performance. And about the root key allocation, you can say we using multiply root key. The root keys used by each GPU through are different, and the size of keys is large. So GPU is used to generate the root keys and store them in the global memory. When using single round key, CPU is choosing to procalculate this round key to improve the speed of execution. So the whole parallel process of SM4 shown in this figure. First, random generate the input and the key according to the laws of input and the key that you need, and allocate memory, allocate the size of block and grid. Then, the random key will be generated by GPU or CPU according to the multi-key or single-key mode. Finally, the data is copied to GPU and the corner function is called for encryption and decryption operations, and then the result is copied back to the CPU. Okay, you can see the environment of experiment in this paper is as the table. The GPU is 10x. The performance of SM4 based on CPU and GPU is tested under the same set of input. Performing 5 tests, then the average value is computed to reduce the error. All tests consider a single round key as a round key. And we use speed operation S to express the improvement of parallel performance of SM4. The calculation equation is defined as this. You can say it is Ts divided Tp. We can see from the figure when the size of input is small, the acceleration ratio of the GPU is not very obvious, and the increase is slower. The reason is that the data transmission between the GPU and the CPU wastes time when the data is not so big. At the same time, GPU can't call enough computing units to perform parallel operations, so the improvement of performance based on GPU is not obvious. However, As the size of input increases, the speed of operation increases rapidly. But when the size of input reaches a certain value, that is 256 kb, the growth of the speed operation begins to level off again, and finally stabilizes at about 15. This shows that the acceleration of GPU is not unlimited growth. It will also be limited by its own hardware. In order to make better use of GPU performance, the next session we will take measures to optimize the operations. Okay, for data transmissions optimization, the measure we adopt are using page-locked memory instead of pageable memory. We can see the difference of these two memories from this picture. By default, the CPU allocates pageable host memory. The GPU can't direct access data in the pageable memory because the memory data might be shifted or destroyed. It can't safely use the physical address of the host memory. The GPU needs to perform two-part copy operation to obtain data from the pageable memory, but by using page-locked memory to allow GPU to access the memory directly, the time of data transmissions can be reduced. Also, the allocation and release cost of page-locked memory is higher than that of pageable memory. It can provide higher transmissions throughput for large-scale data transmission. Figure 7 shows that the performance comparison between pageable memory and page-locked memory. It can be seen that when the size of input is small, the acceleration effect is not obvious. The reason is that the initial cost of page-locked memory is basically the same as the benefit from processing data. However, when transmitting more than 64 kb input, as the size of input increases, the cost of the initial overhead becomes smaller and smaller, and the page-locked memory gains obvious. The final optimized performance increased by 14.73%. The next, for the optimization of the uh, sequential execution of data transmission and kernel operations, the solution we propose is using CUDA system to overlap data transmission and kernel operations. The basic structure of SM4 encryption program consists of three steps. 1. Copy the plaintext and key from the host to the device. 2. Perform the encryption operation. 3. Return the ciphertext from the device to the host. In order to achieve overlap operations, instead of copying the input date to the GPU all at once, the idea of divide and conquer is adopted to divide the input date into multiple subsets. Then each subproblem is independent and can be separately arranged in the CUDA system for calculation. The output transmission of one stem overlaps the core calculation of another stem. we can see that from this figure. And in order to make better use of to replication energies of the GPU, we use 8 stems and 1 cube for each stem for overlapping operations. As a result, the optimized performance increased by 33.3% after this uh, optimization operation. You can see that in this picture. And the performance of the original GPU parallel algorithm has been improved by twice. In the end, compared to SM4's CPU serial algorithm, GPU parallel algorithm has nearly 19 times the performance improvement as shown in figure 10. Compare the final optimization result of this article with other. The speed operation in our scheme is 89, which is higher than the two other respectively, as shown in the table. But because of we use different GPUs, so the high speed operation in our article might be caused by the better performance of the GPU itself. Therefore, we compare our results of throughput with different two. The GPUs they use are better than us. We found that our throughput is middle of all. It shows that our work does effectively improve the performance of SM4. Although our result is not the best, our scheme is still competitive when the price cost is considered. Okay. After analyzing the experiment, it's found that the main factors affecting GPU performance are as follows. 1. The data transmission between the host and the device takes a long time. 2. The sequential execution of data transmission and kernel operations cause the time wasted. Well, the last part is the conclusion. Based on the CUDA under the Linux, we implement the SM4 in parallel and explore the computation of the performance of the CPU and the GPU under the same playtest in the range of 2 KB to 256 MB under the CPU and the GPU. The results show that the GPU performance of parallel implementation of SM4 is almost 19 times faster than the CPU. Moreover, through introducing the page-locked memory and the CUDA stems, the performance of our parallel algorithm can be further improved with the throughput 31.41 gigabits per second. Oh well, the above is all my presentation. Thanks for your time. Thank you.
Hello everyone, my name is Shoichi Hirose. I'm at the University of Fukui. The title of my talk is Another Algebraic Decomposition Method for Masked Implementation. Let me begin with background. Side channel attacks are a serious concern for implementation of crypto systems, and masking is a countermeasure against it. D-order masking splits internal variables into d+1 shares, satisfying that the internal variable x is equal to its shares from x1 to xt+1. And masked implementation processes computation with shares. And masked implementation is often discussed for block ciphers. So let's see operation in GF2 to the n. Then the required number of operations is order of d for addition, scalar multiplication, and squaring. On the other hand, for multiplication, the required number of operations is order of d square. So, for efficient implementation, it is necessary to reduce the number of multiplications. And this page shows some pieces of related work. The first one is by Ishii, Sahai, and Wagner in 2003. They presented higher order masking method for multiplication over GF2. And after that, Revine and Proof in 2010, they generalized the method by Ishii et al. To any finite field multiplication and applied it to AES S-box. Then Khaled et al. Presented the generic method for masking any S-box based on cyclotomic classes and Knuth-Eve polynomial evaluation in 2012. And after that, Coron et al. In 2014 presented heuristic but generic method for masking any S-box. And then Gudarji et al. In 2017 generalized the method by Coron et al. And treated any S-box as tuple of polynomials over a Cartesian product over subfield. And the last one is different from the previous pieces of work. And Khaled et al. In 2015 proposed a heuristic method to decompose any S-box using polynomials having low algebraic degrees such as 2 and or 3. And this page shows an overview of our contribution. We are inspired by the method by Khaled et al. And the method by Gudarji et al. And we propose heuristic method to decompose any S-box using special type of polynomials having low algebraic degrees. And we call the special type of polynomials generalized multiplication polynomials. We call the polynomials generalized multiplication polynomials because masking for multiplication can be applied to these polynomials. And we see that it is more efficient than masking for polynomials with low algebraic degrees. Okay, before going to the details of our proposed method, let me introduce some definitions. This page shows functions of a finite field. In this talk, n is assumed to be an even integer, and n is equal to 2 times nu. And h is a function with n-bit input and n-bit output. Then h can be regarded as a function of a GF2 to the n. Then h can be represented by this polynomial. And for this polynomial, the exponent k is an integer from 0 to 2 to the n minus 1. And the algebraic degree of h is defined to be the maximum of the Hamming weight of the binary representation of k with coefficient alpha k is not equal to 0. And h can also be regarded as a function over the Cartesian product of gf2 to the nu, then H can be regarded as a tuple of functions h0 and h1, and each of them is represented by this polynomial. And for this polynomial, the exponent k0 and k1 are integers from 0 to 2 to the nu minus 1. And this page shows linearized polynomial, and this is definition. Here the function L is over gf2 to the nu, and it is called a linearized polynomial if it can be represented by this polynomial. And the exponent of x is 2 to the k, and k is an integer from 0 to nu minus 1, so the algebraic degree of a linearized polynomial is 1. And for any linearized polynomial, this equation holds. And this equation implies that dth order masked implementation requires d plus 1 evaluations of L. And this shows generalized multiplication polynomial, and this is definition. And M is a function over the Cartesian product of gf2 to the nu, and it is called a GM polynomial if it can be represented as a tuple of functions m0 and m1, and each of them is represented by this polynomial. And here, the exponent of x0 and x1, 2 to the k and 2 to the l, and k and l are integers from 0 to nu minus 1. And for any generalized multiplication polynomial, GM polynomial, M, this equation holds. And we can see that for multiplication, similar equation, this one, also holds. So, due to this property, for the generalized multiplication polynomial, masking for multiplication can also be used. Okay, let me go on to our proposed method for algebraic decomposition. Actually, it is similar to the method by Cadet et al. Except for the use of GM polynomials, generalized multiplication polynomials. And this is an overview of the algorithm of our proposed method. Here, h is a function with n-bit input and n-bit output, and this is a given function to be decomposed. And for this input, first, this method generates component functions and then search functions to represent h using the component functions. And if this search fails, return to step 1. And for this method, once the search in the second step is successful, then the same component functions can be used for any function h. And this page shows the detail of our proposed method. The first step, generation of component functions. This consists of 3 steps. The first one is select all GM polynomials f1 to fr uniformly at random. So, since fi's are GM polynomials, fi can be represented as a tuple of function fi0 and fi1 with domain gf2 to the nu. And then define g1 to gr by using f1 to fr in this way. G1 is equal to f1 and g2 is composition of f2 and g1, and 4 linearized polynomials L00, L01, L10, L11. They are chosen uniformly at random. And for I greater than or equal to 3, gi is composition of fy and gi minus 1. And define q1 to qt in this way. Qj's can be can also be represented as a tuple of functions qj0 and qj1, and each of them is represented in this way. Here gi are used, and ljib, lj0b0, and lj0b1 are linearized polynomials chosen uniformly at random. So they are the first step. And this shows the second step, a search step. So for given function h, it is also a tuple of functions h0 and h1 with domain with range gf2 to the new. And for this polynomial search, tgm polynomials mu1 to mu-t, and these linearized polynomials and constant delta b satisfying this equation. Here qj's and gi's are functions generated in the previous step, and this is gm polynomial, and they are a linearized polynomial, and this is constant. And please notice that I omit the details, but search is to solve a system of linear equations over gf2 to the new. And this decomposition method uses r plus t gm polynomials for any given function h. And this page shows amount of computation based on a proposed decomposition for any h with n-bit input and n-bit output. This table shows that this is the required number of GM polynomials, and they are the required number of linearized polynomials and additions respectively. And please notice that both linearized polynomials and additions are over gf2 to the n over 2. And this table shows achievable parameters minimizing r plus t obtained by some computer experiments. And for input length n, if for the case that n is equal to 4, 6, or 8, they are optimal parameters minimizing r plus t. And for the case that n is equal to 10, they are the lower bounds, minimizing r plus t, 43. These parameters cannot be achieved, but this value, these parameters resulting in r plus t is equal to 44 is obtained. And they are the required number of GM polynomials, linearized polynomials, and additions are computed from these formulas. Okay, this page shows comparison with other methods, and this table shows comparison of achievable minimum number of nonlinear functions, and this is the required number of quadratic polynomials of the method by Khaled et al. This is the required number of multiplications of the method by Gudaji et al. And this is the required number of GM polynomials of our method. And these are the numbers for the input lengths 4, 6, and 8. So from this table, for number of nonlinear functions, for the required number of nonlinear functions, the method by Khaled et al. Is best, and ours is second. You can see that these values are smaller than these values. And for total table size, the method by Gudaji et al. Is best, and the method by Khaled et al. Is second. And please notice that the nonlinear functions, these nonlinear functions can be efficiently tabulated for n at most 8, and the method by Gudalji et al. Only requires a single table just for multiplications. On the other hand, other methods, the method by Caret et al. And the method requires, for example, if the number of input is 4, 3 different tables are required by the method by Caret et al. And our method also requires 3 different tables for each GM polynomials. And from this result, please see this relation. The question is, if our method is worse than the method by Caret et al. And actually, the answer is no, as we can see in the next page. And this page shows complexity of this order masking. And as this table shows, masking for GM polynomial is about twice as efficient as masking for quadratic polynomial. And you can see that they represent the required number of evaluations of these polynomials and the number of random sequences for this order masking and the required number of additions. So you can see that these values are about half of these values. So for masked implementation, our method is more efficient than the method by Caret et al. In terms of the required number of nonlinear polynomials for the case that n is equal to 4 or 6, and for the case that n is equal to 8 if d is greater than or equal to 2. Okay, now let me conclude the talk. We are inspired by the method by Caret et al. And the method by Gudalji et al. And we have proposed heuristic method to decompose any S-box using GM polynomials instead of general low algebraic degree polynomials. And we see that masking for multiplication can be applied to GM polynomials, and it is more efficient than masking for low algebraic degree polynomials. So GM polynomials may enable more efficient masked implementation than general low algebraic degree polynomials. And future work includes performance evaluation by implementation and more efficient decomposition using GM polynomials. That's all of my presentation. Thank you for your attention.
Hello from the EAI team. We have a great new feature in the EAI Compass that you can use. Upvote your favorite presentations to show appreciation and respect to the best presenters. Open up the EAI Compass, go to the program, find the presentation you want to upvote, and hit the thumbs up button. It's that simple.